There we go. Okay, so with our warm-up today, right, we were asked to find out if we can use the mean value theorem or not. And if we can, we need to find the value of C that satisfies the mean value theorem. Right? And if we cannot, we just explain why not. So looking at this function right here, if you look at x equals to 0, which is in this interval from -4 to 1, right, I can say that the function is going to be equal to 0 squared minus 1 over 4 times 0, which is going to give me minus 1 over 0, which is undefined, which means the function is not continuous there. The function is not defined there, right? So y is not continuous, right, at x equals to 0. Therefore, right, cannot use the mean value theorem, and that's it, right? What if there's a number in the denominator? Well, that's a great question, Max. What if there's a number in the denominator, meaning there's no variable in the denominator? It's just 4 in the denominator, and the numerator is 0. Oh, I got you. So let's say you evaluated something, and you got 0 over 5, right? 0 over 5 is perfectly fine, Max. 0 over 5, that's just equal to 0. Yeah. It's when we have a 0 in the denominator. It doesn't even matter if the top is a 0 either. If you have something that comes along the line of like 0 over 0, that's also undefined. I know as weird as that sounds, 0 over 0 is also undefined. So we would say, oh, function is not continuous there. And as I was saying earlier in the class, right, some people are struggling to figure out if a function is continuous or not. And for right now, if you need the help, try plugging it into Desmos or a graphing calculator and just looking at the function graphically to see if it's continuous or not. We'll start there. You can actually, once you get more familiar with different functions, you'll know where functions are defined and where they are continuous and where they are not continuous for basic functions. If we have piecewise functions, we have to question where the pieces connect with each other, right? So what I'm saying is this: if I get another function, let's say I was given like a function that said it was like tangent of x. Let's say I was looking at this function right here, right? And I was trying to figure out, can I apply the mean value theorem to this function y is equal to tangent of x on the interval from, I don't know, let's say -pi to pi, right? Let's say I was looking at the function from here to here. Do I know if that's continuous or not? For right now, like if you're unfamiliar with the graph of it, just go and graph it on a graphing calculator and see what it should look like. So let's go over here and let's go on to Desmos real quick and let's graph this guy real fast and just to see what it looks like. Right? If I was graphing tangent of x, I clearly see there are multiple parts of the function that looks like it's discontinuous. There's a bunch of vertical asymptotes here, here, and here. But I'm looking at it just from -pi to pi, right? So let's see, where is that? So one thing you could do on here is you could actually use a brace and you could type in the values that you want your x values to be between. So if I'm going to do this from -pi less than x less than pi, you guys think, is that function continuous or is it discontinuous? Just by looking at it. Does it make sense? Like, this is one thing you could do. You can see like, oh, this function is discontinuous from pi to -pi to pi, right? Now, does that mean tangent is always going to be discontinuous? No. You can clearly see that this part right here, if I was just only looking at this part alone, I could say that it's continuous on this interval right here, right? So if I make the interval a little bit smaller, like let's say it's let's make it pi over 4, let's say, right? It's +pi over 4, right? That's a continuous function. That one works out. That's okay to deal with, right? And then I would be able to use the mean value theorem there. So for right now, if you're still struggling with seeing if a function is continuous or not, maybe try graphing it just to help you out. You kind of develop it as a secondhand skill as the more problems you do, and you'll see it as you go. Anyways, that's enough of me talking about that. So we can't do number 1. Mean value theorem doesn't apply because it's not continuous at x equals to 0. And then you can stop there. You don't have to say anything else. I know that differentiability is the second part you need to make a comment about, but we only focus on that if we are, if we can say that it's already continuous. Anyways, I'm talking too much. Let's go to number 2. Number 2, is a cubic function, right? And we're looking at it from 0 to 3. Cubic functions is a polynomial functions, and hopefully you guys remember polynomial functions are continuous on all real numbers, and it's differentiable on all real numbers as long as there's no radicals involved. Usually with the radicals, you risk the chance of having a cusp, but no radicals involved here, no cusps in here. A cubic is just going to look something like that, which is continuous and differentiable. Again, if you're having trouble seeing it, graph it and take a look. Okay, so yeah, from 0 to 3, yes, this is continuous, checks out. Yes, this is differentiable, checks out. Since both of those check out, I can say the mean value theorem applies, right? We can do that for this problem. So how does the mean value theorem work, right? The mean value theorem tells you that there is a tangent line between 0 and 3 that's going to have a slope that's equal to the slope of the secant line, right? That's all that's saying. So if the graph looks something like that from this point to this point, here's my secant line that goes like this. The mean value theorem is just guaranteeing that, hey, somewhere between there should be a tangent line that is parallel to it. And it's our job to find it. Okay, it's our job to find it. Let's go ahead and do this out here. Let's do a couple things here. So first things first, let's find the slope of the secant line. Right, the slope of the secant line is going to be equal to f of b minus f of a over b minus a. Right, and your b and your a is your interval, and your f of is just the function evaluated there. So I'm going to go ahead and calculate this guy right here. F of b is going to give me, these are going to be pretty big numbers, huh? I'm going to cheat a little bit. I'm just use my calculator to do this one for us. You guys remember I showed you guys how to do this as a shortcut on a calculator. You could just do it by hand, but I'm just going to do it this way because I'm being lazy. I'm going to plug in this function right here, negative. Make sure you notice that I didn't push the minus sign for negative. I pushed the negative sign down here at the bottom. If you don't do that, you'll get an error. So negative right there, this is going to be x cubed, right? X cubed, bring that back down, plus 3x squared, right, minus 6. So that function is being plugged right in there for y1. I'm going to go ahead and hit second quit, and I can actually have it do the evaluations for me here. So I can go ahead and hit alpha trace, which is f4 right there, and then tell it, hey, call the function that I just plugged in earlier, and can you guys plug in, looks like 3 for me to get the b value, and that's going to tell me that, oh, that being plugged in and evaluated at 3, I get negative 6 right there, minus, let's do the same thing for a, right? Let's do the same thing for a. So I'm going to have here alpha trace, recall that function again, but I want to this time evaluate it at 0. And when I evaluate it at 0, it also comes out to be negative 6, which is perfectly fine. And in the bottom here, I have 3 minus 0. So that tells me that the slope of this secant line is going to be equal to negative 6 plus 6 divided by 3, which is just equal to 0. Right? And Max, hopefully this one answered your question right here. This is one where you would get 0 over 3. So a 0 over the denominator is just 0, right? So that's that guy right there. So that's the slope of the secant line. And I'm now being asked to figure out when is the derivative equal to that, which means I need to find the derivative and set it equal to that. Right? So y prime is equal to negative 3x squared plus 6x. Right? Have you guys become masters at taking derivatives yet? Right? Hopefully you guys have. No product rule needed, no chain rule needed for this one though. Right? Very easy one. Set these guys equal to the slope of the secant line. So I have here 3x squared plus 6x is equals to 0. You could either solve this by factoring or solve this by using the quadratic formula, but quadratic formula will be a little overkill for this one. I'm going to factor out the 3x, negative 3x, and what's left behind is x plus, it's not plus, knock me. You factor out a negative sign, so it should be x minus 2. Pay attention. You're right, knock me. Let's go. So I have here negative 3x is equal to 0, which means x is equal to 0, or x minus 2 is equal to 0, and the other one is going to be x is equal to 2, right? The mean value theorem wants it to be between that, so this is actually the only answer I really care about. X equals 0 is technically included with this interval right there, but it's at the end point of it. And traditionally, when you do these problems, you don't actually include the end point as part of your answer. If you do on my test, I'll give it to you. I believe on the AP exam, they don't include it. I'm just letting you know that right now. They don't include that as one of the answers because it's on the endpoint of it. Yeah, it's a weird one. It's a weird one. So if it was x equals 3, it wouldn't count. Yeah, I would. On the AP exam, they would not count it. But for my test, you did the work and you get there. I'd give it to you. I would be lenient about it. But on the AP exam, they don't like including the C values is what they call it for the mean value theorem. X equaling to 2, that means C is equal to 2 is where this occurs. And they don't like it when the C value is on the endpoints. They want it in between the endpoints. I know it's weird because it's like, but Nachman, it's clearly closed and we're supposed to include that. But yeah, there's a better explanation there, but I don't actually have it on hand and I don't want to tell you the wrong idea. But that's these problems in a nutshell, guys. Rolle's theorem is the last thing we learned, and Rolle's theorem is very similar to the mean value theorem. It's just this right here is actually Rolle's theorem being applied because it looks like f of a is equal to f of b, right? So this is actually Rolle's theorem being applied. But that's what I mean by I'm upset by this guy who gets his name after this theorem because it's just the mean value theorem with a special case, right? Anyways, that being said, that's it for this problem. Let me know if you guys are okay with this, right? Let me know if you have any questions on applying the mean value theorem or Rolle's theorem, right? It's a little strange, but once you get the hang of it, it's like one of those things like, that's it. Yeah, it's not that bad. Not that bad. I'd say this though for your homework. We were doing one problem in my office hours yesterday, and the algebra behind solving some of those problems was a little messy. So if you are uncomfortable with solving certain equations, you got to practice your algebra skills. I think when I was looking at the problem yesterday, one of them was like it had like a fraction with the variable in the bottom, right? So I think we came across a problem that looked something like this. I think we had one where it was, I'm trying to remember this correctly. I think we got one that was like 4x to the 2/3 plus 8 over x to the 1/3 was equal to 0. And the student who came by was struggling on solving this. And then, like I said, the solving this part, solving an equation like this isn't calculus. This is something you practice doing in pre-calc or even algebra 2. Yeah, algebra 2. You would solve rational functions like this. Would you guys know how to solve this? Does anyone know? What technique would you do to solve something like this? This is not related to the warm-up problem, by the way. This is just, let's say we took a derivative, we got this, and we set it equal to the slope of the secant line, and this is the equation I end up with. And I'm trying to find out what does x have to equal for this to be true. Does anyone have any ideas how I would solve this problem? What's something I could do to try to solve this? To try to solve for x, I should say. I'm no longer asking for calculus right now. I'm asking your algebra skills. Anyone got any ideas? What should I do? Stare at you guys awkwardly. What should I do, guys? Any ideas? Any ideas? Rewrite x 8 over x to the 1/3. You could rewrite it. You could. Thank you, Brian, for actually coming up with something. And we could try that. We could try rewriting it as x to the 2/3 plus 8. If I rewrite it, you can rewrite it this way using negative exponents. But I can't combine that because they're not like terms, right? I know they both have the same base, but since they have this different powers, I can't combine that. That's like combining x to the 3rd and x to the 2nd, right? I can't do that. So rewriting it is something we could try, but it doesn't actually take me anywhere. So that doesn't really help us out, so we can't go any further with that one. What else? Multiply both sides by x to the 1/3. And that's actually the technique for this one. If you hate rational expressions, algebraically speaking, you could get rid of fractions, right? By multiplying by the denominator. Multiply both sides by x to the 1/3, and this is going to distribute to every single term, right? So x to the 1/3 times 0, that's still 0. This right here, this is the part that's interesting. X to the 1/3 times this term right here is going to cancel out the x to the 1/3, and you're going to be left with just a plus 8, right? Now this part is also interesting right here. X to the 1/3 times 4x to the 2/3. Do you guys know what you do with your variables that have the same base multiplying together? What is x to the 1/3 times x to the 2/3 is going to be, what do you do with your exponents? Monica, Brian, Juliet, all of you, right? You add them. So this is going to become 4x to the 1, right? Because 1/3 plus 2/3 is 3/3. 3/3 is just 1. And look at that. When you multiply that out, you end up with 4x plus 8 is equal to 0. I'm not even going to finish this problem. This just becomes a two-step equation, right? And that's the part that I need you guys to get into and understand. Like, it's not only testing your knowledge of your new knowledge of these calculus topics, but it's also testing your old knowledge of, can you solve these equations, right? And I don't think that's the important part I'm going to say for calculus. It's just there. It's one of those things like, if you can show that you understand the calculus part, but your algebra skills are a little old, you'll still get, I'd say you still get you'd still get a good passing grade, I'd say, on the AP exam. It's not the calculus that's hard, it's the algebra that's going to be a little trip up for you. That was one of the main things. Anyways, that's enough of me rambling. Let's go ahead and move on to the day's notes, right? Today, we're going to be talking about connecting f prime and f double prime with the graph of f, right? Connecting those guys together. So if you guys want to, that's the title of today's notes for 4.3. If you guys want to, get that down. And then we're going to go ahead and jump into the notes right here. So let's go ahead and do that real quick. So let me go ahead and get my ruler out here. I wanted to show you this right here real quick. So let's draw something like this, right? And I'm going to draw a function right now, just a random function, okay? So here's my random function. It's going to be on the interval from A all the way to B. So here we go. We're going to have something that looks like this. You ready? So here's my function. It's going to go like this. It's going to go up and flatten out, and then curve back up here, and then come back down like so. And then maybe make a little cusp like that, and then come back down to here. I'll give you guys a second to copy that down. So this is just a random function. This is a random function. This is going to, let's call this function f of x. You guys okay? I'm just drawing a random function. I don't actually know what the equation is for this thing. I just know what it looks like, right? Now, we've learned a couple terms here. You might have seen it in the homework. There's some terms that are called like extremas, right? Which is basically another way of saying like maximums or minimums, right? And we also said things like absolute max, absolute minimums, and then we also said things like local max and local minimums, right? Absolute can also be interchanged. Some books use the word global max and global min, and you can only have one global max and one global minimum. It's the ultimate, it's the absolute maximum, the absolute minimum. But there's other terms you can learn which are called local maximums and local minimums. And those guys you can have multiples of. You can have more than one max and you can have more than one minimum. But in your homework, you were asked to do this. You were asked to find a absolute extrema, right? So for this particular problem, I'm hoping you guys can see this right here, that this right here is considered a global minimum, right? Global minimum. Where's the global minimum occurring? It's occurring right there. You see that? Right there. Whereas this right here, this point right here, right? We would say that is a local minimum. Local minimum. It's the low point for everything locally around it, but it's not the absolute lowest. It's not the global lowest. It's right. It's not the absolute minimum. So that's right down there. Where's the absolute maximum or the global max? I would say that's up here. The global max, right, occurs at this point right here. This point right there. Right? That's that guy right there. Now, do you guys see a local max anywhere? Right? Hopefully you guys can see it. That's like right here. This guy right here. We're going to call that right there the local max. Right? The local max. Now, these points right here that are in between, or that are in the middle, they're occurring at critical points. I don't know if you can tell this or not, but at this point right here, right? This point right here, let's call that C for right now. Let's call that C. That's a critical point, isn't it? I'm hoping you guys can see that. If I were to look at the tangent line, right, as I'm going along this function right here, it's going to here, it's going like that, and then when I get up to here, the tangent line kind of flattens out to 0 right there, right? And when it flattens out to 0 right there, that means that the derivative is equal to 0. That means that, well, let's write that down. The derivative is equal to 0, right? Which means that we have a critical point there. We have a critical point there, right? But that's not the only critical point we have, right? Do you guys see where the other critical points might be occurring? Right, I have another critical point right here, don't I? Let's call this one C. Let's call this one C2. Let's call this one C1, just to make it easier for us to mark along the way, right? But yeah, down here at C2, we also have the derivative right here equaling to 0, right? The derivative right here equals to 0, right? But there's a couple more critical points on there, but it's not as easy to see. Easy to see. Anyways, there's actually one critical point between A and C1. I don't know if you guys can see it or not, but there is a critical point right about there. I didn't draw that very well. Hold on a second. I'm going to cheat a little bit. Give me 1 second. There we go. Yeah, there we go. That should work out a little bit better. There. Okay. And that's not actually a local minimum or a local maximum, right? Oh, undo. Right? That right there is just a critical point. That's also where the derivative, right, is equal to 0. And that's another critical point. Let's call that critical point 3. Right? That's another critical point. I have another one that's similar to that, and that's over here. If you guys look at it, this right here, the derivative is also equal to 0 at this point. Let's call that critical point 4. And last but not least, hopefully you guys can see this one as well. This point right here, right? That's another critical point. Let's call that critical point 5. Right? But that one, the derivative is not equal to 0. Can you guys tell me what's the derivative at that point? Do you guys remember? Critical points not only happen when the derivative is equal to 0, but it's also where the derivative is undefined. That's right, Monica. It's undefined. Grace, that's all. F prime there is undefined. How do you know it's undefined? How do I know the derivative there is undefined? It's a cusp, right? There's no local linearity there, okay? So looking at this graph, right, derivatives tell you quite a bit of information, right? If you have a derivative equaling to 0, you have a possible local max or a possible local min, right? You could even have a global max, right? You just have to test the points and see what values come out of there, right? So that's one piece of information there, but not all critical points are guaranteed to be a local max or a local min. Do you guys see here at at critical point 3 and at critical point 4, we have the derivative equal to 0 there, right? If I look at those tangent lines and I took this ruler and I got right here and I was like, hey, what's the tangent line here? What's the slope of this tangent line right here? And you'll say, oh, the slope of that tangent line is 0. It goes flat right there. But it's not a minimum and it's not a maximum. That's because it has some points that are lower than it on this side, so it's not a local minimum. And there's some points that are higher than it that's right around it, so it's not a local maximum. So it's neither. It's just a critical point, but it's not a max or a min. So we need to kind of deduce, like, well, how can you tell if something is a max and something is a min then? Well, take a look at this local max right here. Take a look at this local max right here. All the points that are to the left of it, right, are a little bit lower, and all the points that are to the right of it are also all a little bit lower. But I don't want to go there and like, I have to plug into the function and see what the value is and see if it is lower than that and then test it to that critical point and see what that value is. That's too much work. Instead, if we look at the derivative value, it actually makes it a little bit easier to see if something is a max or a min or not. You ready for this? If I go through each of these parts of this function, right, would you guys agree if I look at the slope of the tangent line from A to this critical point 3 right here, all of these tangent lines have a positive slope. You see that? It's positive, 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 all the way up until the critical point. So this interval right here, from here to here, I would say that the function is increasing. But not only that, I'm going to say that the derivative is positive, right? The derivative there is positive on that interval. And then right here to the next side of it, I would also say that the derivative here is still positive, right? If I look at the tangent lines right here, it's still increasing all the way up to here, all the way up to here. And then once I get to this part right there, the derivative is no longer increasing. The derivative now changes. This tangent line now starts to go down. The tangent line starts to be going like this, which means the function is decreasing. I'd say the derivative itself is negative. Are you guys okay with this notation, by the way? F prime being greater than 0 is just another way of saying positive. You guys okay with that? And then F prime being less than 0, that's just another way of me saying negative. Okay? All right, so that's the derivative on that interval. And then I keep going along here. This now is changing up, and its tangent line is now positive on this interval. Right? F prime is now positive, which means it's greater than 0. So F prime greater than 0, right over here. This one is going back to like this. It's going down. So right there we have F prime is less than 0, meaning it's negative. And over here, F prime is less than 0 right there. So I know there's like a lot of information here, and we're going to break it down piece by piece. Okay? But when you're looking at the derivative, I don't know if you guys can see this. Derivatives will help you find critical points, and critical points are key. They tell you like, oh, you might have a local max there, you might have a local minimum there, right? But the first derivative also tells you when is a function increasing and when is a function decreasing. And functions are increasing when the derivative is positive. Functions are decreasing when the derivatives are negative. You see that? Negative here and here. So whenever the derivative is negative, you can kind of see the original function is going down. When the derivative is positive, you can kind of see that the original function is going up. See how it's increasing from here to here, here to here, and here to here. And wherever it's negative, it's decreasing. It's going down there, and it's going down from here to here. Hopefully you guys can make that out. So those are the three pieces of information that actually comes from you taking the first derivative. Okay? And I'm going to write that down for you guys. All right? We want that in our notes here. So the first derivative test, or I'm going to say first derivative chart. Table? First derivative table. Yeah, first derivative. Let's go with table. The first derivative table contains, this is what it contains, right? Number one, the critical points. Critical points, right? Which basically is where the derivative is equal to 0, right? Or it's undefined. Second thing it contains, the intervals where the function, the original function, not the derivative, the function is increasing. Where the function is increasing. And this occurs when f prime of x is positive. Where it's positive. Right? We have that in the chart. Wherever f of x is positive, the function is increasing. Right? And the last thing that it also contains is the intervals where the function is decreasing. Where the function is decreasing. And that's going to happen where f prime of x is negative. Where f prime of x is negative. And that's occurring right there. Okay. I know this sounds like this list of things is kind of weird, but when we actually start doing a problem, you'll realize it's actually not too bad. And then we're not going to finish today, of course, but hopefully we can get into more of it. But let's have this here, and let's go ahead and do a problem. Okay? Let's go ahead and do a problem. So you guys got that down? If not, right, open up the notes in the in OneNote, and you can go at your own pace and copy what you need. So let's take a look at an example problem on how we do this here. Okay? Let's take a look. Give me a second here. There we go. So let's go ahead take a look here. Let's say I was asked to, here we go. So I was asked to find the local extrema for, and here's the function, f of x is equal to x cubed minus 12x minus 5. Let's see if you guys can get that down there. So local extremas are possibilities at specific critical points. So whenever you're asked to find local extremas, right, you need to find critical points. Now, once you find the critical point, that doesn't guarantee that those critical points are maximums or minimums. They're possible max, they're possible minimums, right? So these critical points are going to occur where the derivative is equal to 0. So that means whenever you're asked to find an extrema, you need to find the derivative. So for these types of problems, the first thing you need to do, right? Step 1, find the derivative. Find f prime. So we're going to do that real quick. F prime of x, take the derivative of this guy, is going to be 3x squared, right, minus 12, and the derivative of 5 is just going to be 0. So there's my derivative, right? 3x squared minus 12, right? Step 2, set f prime of x equal to 0, which is just a fancy way of saying find the critical points. Find the critical points. That occurs when your derivative, 3x squared minus 12, is equal to 0. And again, we got to get into this whole, like, how's your algebra skills? Do you guys remember how to solve this quadratic, right? Do I need the quadratic formula? Do I need to factor? Or can I just solve for x straight up? Because it's just x squared, right? There's no other x terms in here. And I'm hoping you guys are remembering your abilities here. I'm going to add 12 to both sides. I end up with 3x squared is equal to 12. Divide both sides by 3. X squared is equal to 4. Take the square root of both sides. I'm going to be ending up with x equaling to plus or minus 2. Does that mean that negative 2 and positive 2 are both maximums or both minimums, or one's a max and one's a min? I don't have enough information to figure that out. What I need to do is create a table, right? I need to create a table. So I plug this into a table, and I use these values right here. I use x equals to negative 2 as one of my values, and I use x equals to positive 2 as another value. Now, when I plug those in, I'm looking at it at the values of the derivative. That's what I'm trying to look at. I'm trying to plug in these guys into the derivative and see what I get. I don't have enough space here. There we go. So I'm plugging this into f prime of x to see what I get. Now, I'm not going to plug in negative 2 into the derivative. Do you guys know why? If I plug in negative 2 into the derivative, you guys know what I should get, by the way? If I plugged in negative 2 into the derivative, what's going to come out? I just solved it, right? And I got negative 2 and positive 2. What do I get if I plug that into the derivative? You guys have any ideas? Try plugging it in. What do you guys get? Brian, that's right. You get 0 because we literally just solved it for when does it equal to 0. And positive 2 and negative 2 give you 0 because that's what we solved for. So that doesn't tell me much. That just tells me that it's a possible maximum, possible minimum. What I'm going to do instead is pick numbers that are less than 2. Someone give me a number that's less than, I'm sorry, not 2, less than negative 2. Someone give me a number that's less than negative 2. That would be easy to plug into the derivative. What's a negative number? What's a number that's less than negative 2 that would be easy to plug into the derivative to evaluate? Anyone? What's a number that's less than negative 2? Negative 3. I like it. So I can try over here. Let's go ahead and try evaluating this. F prime of negative 3. See what I get, right? So I evaluate that in here, and I get here 3 times negative 3 squared minus 12. Negative 3 squared is going to give me 9 times 3, which is going to give me 9 times 3 is 27, minus 12. I end up with f prime of negative 3 being equal to 15, which means that my derivative, right, for everything less than negative 2, my derivative values for everything less than negative 2 is going to be a positive value. that means my function, f of x, is increasing here. Can you guys picture what the function f of x is looking like then for everything less than -2? If everything less than -2, that means the function is going up. I don't know where it's going up. I don't know if it's going up from down here or if it's going up from up there. I just know that it's going up, right? So what does that mean? That means my function is doing something like this. It's going up until it reaches -2, and then it kind of flattens out, right? And what is it doing after -2? That's what I need to figure out by plugging in another value that's between -2 and 2. Anyone have a good value that's between -2 and 2 that we can plug in that would be easy? Monica's really quick with that answer. 0. 0 is one of my favorite numbers to plug in. Right? They're the easiest ones to evaluate. So I'm going to plug in the into the derivative 0 because 0 is between -2 and 2. And I just want to see what is the function doing between -2 and 2. When I plug in 0, I'm going to get here 3 times 0 squared minus 12, which tells me that the derivative at 0 is equal to -12, which means that it's a negative sign, which means the original function f of x is decreasing on this interval. It's decreasing on the interval from -2 to 2. So once it reaches here, it starts to go down. Again, I don't know where it's going down, but I know it's going down. So since, whoops, let me erase that. So since x is equal to -2 is a critical point, and the function is going up on this side and then going down on the other side, I can say that this right here is a local max. It's a local max. I'm hoping you guys understand why I can say it's a local max. It's increasing on this side, then it's decreasing on this side. That means it has to go up and then come down, which means that that critical point is the highest point for that local spot, right? Which makes it a max. Now, with that being said, let's move over here. What's happening at x equals to 2? Well, the function on this side is going down, right? I just need to figure out what's the function doing on the other side. And a number that's bigger than 2 would help me figure that out to be plugged into the derivative. What's the number that's bigger than 2 that I can plug into the derivative to calculate if this is increasing or decreasing? Monica, Emily, David, all you guys are going with 3. 3 is perfectly valid, right? We plug that in, and we go ahead and see 3 times 3 squared minus 12. That's going to give me, that's 27 minus 12 again. Oh, again, it's going to give me 15, right? Which is a positive value, right? Thank you, Monica. I was drawing a blank there for a second. Yeah, so 27 minus 12 is going to give me 15 again, which is positive 15, which means the function itself is increasing on this interval from 2 and beyond, right? From 2 and beyond, it's increasing. Well, what does that mean? That means that if it's over here, it's going down, and then it changes to going up. You guys see, what's that critical point at x equals 2 going to be? It's going to be considered a local minimum. A local minimum. Yeah, that's right, Brian. Local min. So those are your local extremas. You have a local max at x equals to -2, and you have a local minimum at x equals to 2. And that's it. You're able to get this without actually graphing it, right? You can do it numerically now. You can see where those things occur. And if I were to graph x cubed minus 12x minus 5 onto Desmos, and I want to go look at -2 and +2, it's kind of neat. You ready for this? X cubed, I already forgot the function, minus 12x minus 5. Boom. So here's my graph. And check this out. Look at this beautiful graph. It's going up, then it's going down, then it's going up. Where does it change direction? It changes direction at x equals to -2, and it changes direction at x equals to 2. It's like mind-blowing, I'd say. This is kind of neat. You could do this now numerically. You can calculate these things just by looking at the function and looking at its derivatives. Okay? So how do I know it's a max or a min? The derivative basically changes signs, right? It goes from increasing, which means the derivative is positive, to decreasing, which means the derivative is negative. So if you see a sign change on your derivative, you know that you're going to have either a local max or a local min. If it changes from increasing to decreasing, hopefully that makes sense. It goes up and then it goes down, which makes it a max. Whereas if it's decreasing to increasing, it goes from negative to positive. That means your function is going down like this, and then it changes direction and goes up. that critical point is a local min, right? So that's information that you can draw just by looking at its derivative, right? And looking at its values. Not only where does it equal to 0, but where is it positive and where is it negative, okay? And I think this is the part that trips up a lot of students. They'll say things like, well, Nakmi, you said that from -2 to 2, the derivative is equal to a negative number, but it's positive right here. The function is positive right here, but the derivative is negative. And this is where you guys need to make sure you can see the difference between its function value and its derivative value. The derivative, which is the tangent line, is negative all the way to here, right? It's all the way to here. Whereas the function value itself is positive and negative, right? It's positive and negative. So we got to make sure we pay attention to that. Anyways, I'm going off too much on a tangent again. That's how we find local extremas, just by looking at the derivatives. Okay? So let's go ahead and try another problem. Let's try another problem. Okay? Let's try another problem. Let's go over here. Let's say I was asked to, let's do another example right here, right? And I was asked to, again, find local extrema. Find local extrema. And let's do it for this problem right here. Let's say I was asked to find it for y is equal to x squared minus 3 times e to the x. So remember, right, if I'm looking for local extremas, I'm looking for where the derivative is equal to 0, and I'm looking to see where the derivative changes signs, right? I'm looking to see where does it go from negative to positive or positive to negative, right? If it doesn't change sign, the critical points aren't actually any extremas. Check this out. Before we actually do this problem, let me go back to this beautiful graph I drew for you guys, right? Look at this critical point at critical point 3. C is equal to 3 right here. Do you guys see how this right here, the derivative is equal to 0, but if the derivative was increasing to the left of it and increasing to the right of it is not a max or a min, it's just a flat point, right? A flat tangent line. And same thing over here, right, at C4, right? We have a critical point there, but that's not a max or a min because the signs don't change. It stays negative around that critical point, and over here it stays positive. It only has a extrema if the signs change from negative to positive or from positive to negative. So let's go down here and take a look at this problem right here. So first thing we need to do when you're trying to find local extremas, the very first thing you should do is find the derivative, right? Find the derivative. You can use the product rule, or you can distribute this and use the power rule with the product rule. I'm just going to use the product rule because I already see it right here. If I distribute this, I'll have x squared times e to the x, and I'll need the product rule anyways. So I'm just going to go ahead and start off with the product rule. So first things up, find the derivative. So I'm going to do this using the power rule. I'm sorry, the product rule. This being my first function, this being my second function. Right, I'm going to go ahead and do that real quick. So derivative of the first is going to give me 2x times the second function, which is e to the x, plus derivative of the second function, which is just going to be e to the x, times the first function, which is x squared minus 3. Okay? And that's my derivative, right? To help me find the critical points, I need to go in there and, well, figure this out, right? So I need to find the critical points. I need to figure this out by setting my derivative equal to 0. So to find my critical points, my derivative right here, I'm going to simplify this out. I don't want to, since I'm going to have to solve this for 0, setting this equal to 0 and solving for x, it's going to take a little bit of work here. So I'm going to go ahead and just multiply this out. This is going to be 2 x e to the x plus distribute this guy right here. I'm going to end up with e to the x squared minus 3e to the x. And again, I'm setting this equal to 0 to solve it. And this is what I mean. How good is your algebra skills for this one, guys? How good is your algebra skills for this one? It looks scary, but it's actually not that bad, right? I shouldn't have said it looks scary. It doesn't look that bad at all, actually, if you are calm about it. A monstrosity. Check this out, Max. Every single term that I see there has an e to the x that you can factor out. If you ever have a problem that looks very complicated, Try factoring out a common factor and see if it looks a little bit easier to deal with. E to the x is in all of them. I'm going to factor that out. So I have e to the x factors out, and I'm going to end up here with 2x plus x squared minus 3 equals to 0, which I'm hoping you can see. This right here, I can rewrite it into decreasing powers, right? Descending powers. So e to the x times x squared plus 2x minus 3. And I'm hoping you see that's not that bad, right? That's just a quadratic multiplying with e to the x, right? And I can factor this x squared plus 2x minus 3. Do you guys know how to factor? Do you guys have a particular method you guys want to share with me? I'm going to do it just the guess and check method way, but do you guys have a method that you guys prefer? Box method? I was about to say Korean method. I don't know. I don't think you guys actually had me, so you guys might not know the Korean method. There's also the diamond method or the X method. Yeah, the big X method. Yeah, you can do it that way. Whatever works for you, right? Whatever works for you. Monica's already jumping ahead of me, and she has the factors already. That's good. X plus 3 times x minus 1 equals to 0. So again, whatever method you're familiar with, you are going to have to be able to factor some quadratics along the way here and getting that done right there. So take a look at that problem right there. Okay. Now, from here, we're going to go ahead and use the zero product property, right? And split this up. When do these things equal to 0? When does e to the x equal to 0? When does x plus 3 equal to 0? And when does x minus 1 equal to 0? We're going to have here the critical points going to happen at x equals to 1, x equals to negative 3. And this thing is never going to equal to 0. E to the x is an exponential function that will never equal to 0. There's nothing I can plug into x that will ever make that thing 0. So e to the x is never going to equal to 0. It's still part of the function. It's just not possible to make it equal to 0. So my critical points are going to happen at negative 3 and at 1. So once I found out my critical points, next thing I need to do now is make a table, right? Make a table at x equals to negative 3, x equals to 1, and figure out your signs for your f prime, right? Figure out what is the derivative doing on the intervals around your critical points. I'm not going to plug in negative 3, because if I plug in negative 3, I'm going to already know it's going to equal to 0. I'm not going to plug in 1, because if I plug in 1, I know it's going to equal to 0. So I pick numbers that are around it. I pick numbers that are on the interval that are around it. So here's how you can actually have it help you to figure out what the intervals should be. If I have this as my critical points and I have nothing else, and I have this as my critical point and I have nothing else, the interval that's between the two of them is somewhere between negative 3 and 1. I can pick any number I want between negative 3 and 1. Everything that's to the left of negative 3, I can say, oh, I can go up to negative 3 but not include it, and pick anything else that's less than negative 3, which means the interval is going to be from negative infinity to negative 3. I can pick any number I want from here to test this one. And same thing can be said over here. 1 is the lowest possible point, but it doesn't include it, and I can pick any number that's bigger than that. So these are the intervals that I'll be dealing with. Negative infinity up to 3, I'm sorry, negative infinity up to negative 3, negative 3 to 1, and then 1 to infinity, right? So those are the values I'm going to plug in. Those are the things I can check to plug into the derivative right here. What's a number that you guys want to pick from negative infinity to negative 3? What's a good number you guys want to try? And we got to plug this into the derivative, of course. Negative 4. Why not? Why not? Let's go with negative 4. So f prime of negative 4. I'm going to plug this into the derivative right here. I'm going to plug it into the factored form, by the way. I'm going to plug it into the factored form. Okay? So I'm going to plug that in. And this is going to be e to the negative 4 times negative 4 plus 3 times negative 4 minus 1. Why do I plug it into the derivative? I don't know. I'm just messing around. You could plug it into the actual derivative up here. You could plug it into here if you wanted to. I'm plugging it into the very bottom one right here, and you'll see why right now. Check this out. E to the negative 4 is a positive number, right? E to the negative 4 is a positive number. And this is going to be multiplying with negative 4 plus 3, which is negative 1. That's a negative number. And then that's going to be multiplying with negative 4 minus 1, which is negative 5, which is another negative number. The derivative, I don't actually care what the value is if I'm looking to see where it's increasing or decreasing. Does that make sense? All I really care about is the sign. Now that's why I'm plugging it into here, because I can then see what's a positive times a negative times a negative. What's the end result going to be, guys? Positive times a negative times a negative. It's going to be positive. which means the function is increasing, right? F of x is increasing on this interval. Okay? And that's all I really care about. So I know that it's increasing over here. So there's a good chance that this x equals to -3 is possibly a local max. But I don't know that for sure until I test a point that's between the two critical points between -3 and 1. All right, so let's test the derivative at some number that's between -3 and 1. What's my favorite number that's between that interval right there, by the way, to test? You guys know? What's an easy number to test? 0. That's right. So I'm going to have here e to the 0 times 0 plus 3 times 0 minus 1. Right? So we test this out. E to the 0, by the way, is just a positive 1. Right? Positive 1. 0 plus 3 is going to give me a positive 3. And 0 minus 1 is going to give me a negative 1. So I have a positive number multiplying with a positive number multiplying with a negative number. That's going to leave us with a negative sign, right? A negative number. I don't even care what the negative number is. -3. But I do care the fact that this is telling me that the original function is going to be decreasing. Decreasing? Come on, knock me. Decreasing on this interval, which means it's going down from there to there. So tell me, guys, at x equals to -3, what is it? Is this a max or is this a min? This is a local what? Local max. That's right, guys. This is a local max, is what you just found. Okay, local max. Let's go ahead and finish this off. Give me a number to test out into the derivative after 1, right? On that interval from 1 to infinity. What's a good number to test after 1, guys? What's a good number? 2. 2, why not? We can plug in 2. So we'll have here e to the second times 2 plus 3 times 2 minus 1. E to the second is going to be a positive number. 2 plus 3 is going to be a positive 5. 2 minus 1 is going to be a positive 1. So I have a positive number times a positive number times a positive number, which means my end result is going to be positive, which means that f of x is going to be increasing on this interval, which means that over here it's going down, then over here it's going up. So x equals to 1 is a local minimum. There you go. There is your local extremas. That's how you find them based off of what's given. All right. I want you guys to try one problem on your own to see if you can find out where is there a local max and where is a local min. Okay. Let me write up a problem for you guys to try here. Let me know, by the way, if you guys need me to keep it on the screen. I'm going to go ahead and scroll off it. But again, it's on OneNote, so you guys can click on the link in Canvas if I'm going too fast. Okay. If I'm going too fast, you guys can click on there and you can have it on your own screen. Let's go ahead and find all local extremas. Extrema, right? Find all local extrema for this function right here, f of x equaling to x cubed over 3 minus 4x. You guys go ahead and try this problem. Try this problem on there, and I'm going to clear your pair deck so you guys can do it on there. I want to see you guys attempt this problem here. And yeah, if you've lost your pair deck, give me a second. I'll put that link back in there so you guys can reopen it up. But I do want you guys to try this out. Go ahead and give that a shot. Give that a try. See if you can get the answer for this one. Tell me where are the local extremas and if they're a max or a min on those points. So give that a try. This problem right here. There you go. We only have we only have 4 minutes. So this is what I want. Yeah, before you leave, at least put down an answer or something. Yeah, you have 4 minutes. Give me your answer after 4 minutes, and then we're going to call it there, and we'll go over the answer together next time. But for right now, I do want you to try this. I do want to see your attempt on this. I do want to see it on the pair deck. I'll give you guys participation points for this. We'll consider this like your exit ticket. Yeah, and we'll go over it on Monday. My pear deck is blank. Yeah, it's clear. So you can draw whatever you want on there, Brian. The problem is written on the, oh. Sorry. Yeah, guys, I don't know what you mean. You should be able to do it. Just work it. What's your problem? Sorry, my fault. How about now? There you go. There you go. Juliet, come on now. You don't need to bruh me. You got this. Don't call me out on my nonsense. Just do the work. See, it wasn't a mistake. I was just seeing if you guys were paying attention. That's all it was, right? And good job. You guys were paying attention. You saw that you couldn't write anything. You let me know. So it was a test. It was just a test. Good job. Good job, Brian, Grace, Julia, right? Both Brians, right? It was just a test. That's all it was. And congratulations, you guys passed. I can't believe the class is already over. I had so much more planned activities and just I think I spent too much time with the warm-up today or something. But yeah, let's take a look at what you guys have, and then I'll let you guys know when it's time to leave. But just type what you can. All right. Just in case you didn't have enough time to finish it, I don't want to hold you over time. So the bell's going to ring. Class is going to end in like 20 seconds. I'm going to leave this pair deck open until sometime today. So get an answer in there for me just to attempt it. I'll go back and check it off. And then what you have attempted, I will give you guys credit for. So you will be grading credit for this. So just put in your attempt in there. It will remain open even after the class ends. And I just want to see what you guys get for your attempt for what is your local max and where is your local min, if there is any. And yeah, that's going to be it for me today, guys. I won't see you guys until Monday, so have a good weekend. Get this problem done for me today before the end of the day. I'll give you guys the credit for that. And other than that, guys, have a good weekend. Stay out of trouble. Stay out of jail. Don't get pregnant. All right? I'll see you guys on Monday.